My name is Vivek, and I've graduated with a master's degree in Stony Brook University back in New York, and I'm currently working as a senior software engineer at Microsoft. First of all, thank you everyone for giving me this platform to showcase my presentation on this paper. I'll be going through scalable consensus algorithm for blockchain networks, but more towards establishing a framework for developing decentralized applications for IoT platforms. And during the course of the presentation, we'll see how that comes about as and when we speak. So what is the scope? Today, distributed systems are essentially widely used in any applications that require monitoring and control of physical environments. And I'm speaking specifically with respect to supply chain, factory automation, and IoT, because these kind of environments require interaction with physical environments. So blockchain networks or on-chain networks are a subsection of distributed systems which contribute to this kind of industry. So what are the challenges that we currently face while developing software for these platforms? The first thing is the language itself. The abstraction of the language is inherited from those that are used in standalone applications, which means blockchain being a very recent technology hasn't quite matured enough to provide robust platforms wherein developers can can come in and develop open source softwares or open softwares for a completely decentralized distributed system, which is very different from writing software on a standalone system with a typical client-server interface. So the fact that there is little to no abstraction layer for programming open distributed systems for monitoring and controlling physical environments makes it a challenge to come up with solutions which cater to IoT applications. So what is the need? The need is obviously the fact that we don't have an abstraction for distributed computational nodes or agents. So the need arises from the fact that we need a framework which is robust and established, where something that has been battle tested and is out there for people to build upon, and a precondition effect style of programming, wherein your solution or your code is modular enough, where you're identifying a set of conditions, which when satisfied gives rise to executing a bunch of statements following that. And then you have obviously the idea of coding for a single agent, which deploys on multiple agents. So redundancy in work, performs distributed tasks like leader election, formation, distributed search, distributed SLAM, and so on and so forth. So what does this paper propose then? So this paper proposes a K-framework-based abstraction and interface layer for development cycle, and we'll go into what K-framework and all of that is. This paper also proposes a state machine for the program code. So the new framework that this paper proposes has been passed through a widely accepted state machine called the K-framework, which validates it in the form of results and experiments that we'll see later on. And then a sample simulation of a distributed system, identifying the main components of an agent and the shared resources that are usually very typical of a distributed system with n agents, and then validation in the form of results that, again, we'll see towards the end of the slides. Okay, so before we jump into the solution itself, it's important to identify a few specific entities that, a few specific modules that form a part of this paper, and which will keep coming up as and when we speak towards the course of this presentation. First one being an agent. So what is an agent? An agent is an entity that is executing a PCCL-like program. And for those who aren't aware, let's not get too caught up on PCCL. PCCL is basically an automation language that was developed by CMNs. And this was specifically for automation and control systems. So an entity is basically a node or a resource which runs a bunch of commands. And these commands are PCCL-like in nature, as in they interact with sensors which are interfaced with the node itself, and of course have a communication going on with the external physical environment. And this lives in the controller. And then you have the shared memory. The shared memory, in a real-world distributed system, a shared memory can well and truly be a database which is living away from all of the nodes itself. and there's communication going on between all of the nodes in the distributed system, as well as with the shared memory. And then local memory. A local memory is a memory that is bounded by the boundaries of the node itself. And this can have intermediate computation values, status codes, flags, and things like that. And then, of course, the processing unit of the agent. This is the bare bones chip that runs that's running inside the node. Okay. So what is an event? So when you write code within this node, which lives in the application layer or the controller logic, it's important to identify what an event is. And so a couple of slides back, I mentioned how we needed a way of having a precondition effect kind of style of coding. And that's what an event exactly is. So a program can have a bunch of events, an event 1, event 2, so on and so forth, and number of events mutually exclusive to each other. And each of these events have two specific parts to it. First one is called preconditions, wherein you have a set of conditions which, when evaluated to true, executes a bunch of statements. And that is all that the event does. It has absolutely no idea or knowledge about what the external factors are, what the physical implications are, nothing. So at any point in time, with every cycle, it checks to see if a bunch of flags are evaluated, and if it's true, it executes a bunch of statements. So now that gives rise to the distributed system itself. In a very simplistic form, this is what the system looks like. You have agent I and agent J. This obviously is scalable to n number of agents. But typically, what you're looking at is a very typical distributed system, wherein you have multiple nodes or agents, and then each of these agents are running the exact same program logic. And then you have a controller which is interfacing with that program logic, and the controller is also interfacing with sensors. It can be cameras, it can be temperature sensors, or whatever. And then there's a platform with a shared environment. And the shared environment over here could also be, like I said, a database that is living somewhere in a data center far, far away. So how are we setting this up? What are the constraints or the boundaries within which this distributed system is working under? And what differentiates this distributed system from any other distributed system? Clearly, all agents in the system are executing the same PCCL program, because the goal is the same for the system itself, and therefore for the nodes in the system. Each agent is aware of its peer agents within the system, and the common environment bounds of the physical space within the agents are set for every node. For example, this is something that is currently in experimentation at Amazon warehouses, where a bunch of swarm nodes or robots are currently performing sorting operations in their inventory factory. And this is something that was 5 years ago done very manually by people. So there needs to be some form of knowledge sharing between what one node is doing, and that needs to be propagated to all the other nodes in the system, and that's called swarm intelligence. So we'll look a little bit at what this is sometime later. Okay, so now we can get into the abstraction of the structure itself. So when we write the infrastructure, the infrastructure that's provided in the paper provides a way of abstracting most of these things, which makes it very easy for someone to onboard this infrastructure and write solutions for different kinds of problems as well. You can have robots in an Amazon warehouse. You can also have robots that are doing something else with a whole different logic somewhere else. So the interface is what we are dealing with here. So the first part is the variable declaration. We'll get into each one of these in the following slides, but just in a sense, what this does is variable declaration is the section where you declare the kind of variables that you'll be working with within the system. And these include both shared variables as well as local variables. And shared variables, of course, can also be all read and all write, which means it's a memory space which is being accessed by all nodes in the system, versus all writes, where it can be written by pretty much every node in the system versus just read. And then initialization, like the name suggests, is initializing all of these variables. And then you have the event blocks. The event blocks form the most exciting part of this, and we'll double click on that in a couple of slides. Okay, so the variable declaration itself is broadly divided into three parts: the middleware declaration, the software declarations, and local declarations. Middleware declarations are declarations which happen at the controller level. They are usually in the shared space, in the shared memory bounds, and anything that you touch within the boundaries of an agent in the middleware declaration has to be made sure to be atomically locked, because all the other agents are also accessing the same thing, and you don't want race conditions and things like that. Software declarations. These are declarations that you make in order to have intermediate computations in a given node. And then local declarations are declarations within a subroutine. In this case, within the bounds of a logic space. And these are obviously once used, the garbage collection takes over, and then garbage collection takes over, and they're cleared out of the heap memory. Okay, so each of these variables follow the exact same structure, and that makes it key to figure out how to write how to use the framework basically. So the declaration is a recursive structure. It's a composite pattern. It can have a statement or a bunch of other declarations inside of it. So if it is a statement, it can either be an enum, an array, or a custom type and variable. But it can also have declarations within declarations, and these declarations are recursively executed when the flag conditions are set to true or evaluated to true. And we'll see an example of that in the simulation. Okay, and then the initialization block, we already went over this. It basically just initializes any statements that need to be initialized because the environment wants it to be initialized before logics can run. Okay, this is where the interesting parts begin. Event block, or an event. So initially, a couple of slides ago, we saw that a program can have multiple events, event 1 to event 10, all of them mutually exclusive. Right. So an event block defines a collection of events. So a program module or the logic can have a number of events, each running when a specific set of conditions are evaluated true. And each event consists of an event name, a precondition, and an effect. We saw that. So the pseudocode that I have there is basically it takes the form of a K infrastructure code where you have an event block, and we'll see what K infrastructure is, but we have an event block with a set of events. Each event has a single event or another set of nested events, and every event can have an expression and an effective bunch of statements that get executed when the expression is validated true. And the statements themselves are pretty basic, common to pretty much all high or low level programming languages: assignment statements, conditional operations, loops, and atomic operations. Okay, so finally, what is the K framework? K framework is basically a framework that is well defined and accepted in the industry to validate a programming language using Backus-Naur form of syntax. What that means is, every time we come up with a programming language or a framework for a programming language, it needs to pass through a certain number of tests. And what do these tests represent? These tests represent the way transitions happen within the executing time of a statement. What is the automata that controls the state changes within that statement? And K framework provides that. So we'll be running the framework through the K framework, the proposed framework in the paper through K framework, and we'll see how K framework holds up. A quick example of K framework in play is the statement right there. Now, what you see above is a typical K framework automata. The numerator, or it's not a fraction, but just to clarify, everything that's above the line is what the state is what is the state of the automata at present, and everything below the line is the state of the automata after the execution is complete. So what we're looking at here is basically the first part of the expression, x ... _k. What that means is that there is an expression currently which is being executed, which involves a variable called x. Now we need to figure out what x is. So The next part of the expression does exactly that. It looks up the memory, it figures out what is the value of x, in this case v, and then replaces v as part of x in the statement, and then executes the statement. So the final version of the statement converts to what is below the line, which is v dot 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 underscore k. This is a very simple lookup-based rule, and we'll see more complex rules that the framework supports. But this is just to give us an understanding of what K framework provides. Okay, so we spoke about an agent. An agent is essentially just a node which has 4 components to it. It has the controller, it has its local variables, a shared memory space, so on and so forth. Now, how do you represent an agent within the K framework model? This is a typical agent within the K framework model. K, which represents a bunch of computational nodes within the agent, and then you have the ID, which uniquely identifies the agent, and then you have a memory, which is local memory to the agent, and you have a position, and this position is specific to a specific use case, but this is essentially just an input that is coming in from the external environment. But if you're looking at a robot in a warehouse, it could be position. So positions, which is essentially coordinates, and then a counter. And we'll see what counters and lock states are, but for now, let's just hold that thought. These are local to the agent itself. So since agent can be represented in the K framework, the entire system itself can also be represented as part of the K framework. And how does that look? This is the exact same system that we had a few slides ago, but if we were to convert that into the K framework model, you have multiple agents under the agent node, and then you have a global memory, which is a new introduction here. Global memory is the shared memory that we've been talking about. So this could, in the real world, this represents, again, some kind of database, Cassandra, SQL, you name it. It lives outside of the chain itself. And then you have a memory map. This is a global map or a lookup table for all the available addresses for the entire system. And then you have time. There's a nuance here, which I will get into in the next slide, because time broadly is classified into a discrete time and continuous time. We'll see how that works. And then a counter map. Remember, we spoke about counter in the previous slide, and counter is specific to an agent. Now we have a counter map, which is specific to the system itself. So this is the systemic knowledge of every counter which lives within every agent. And then you have a lock queue and a transition state. This is important when we get to atomic operations and stuff like that. So we'll see when we get there. Okay. So let's take another example of a rule declaration. A couple of slides back, we saw how a rule lookup works. Now, this is what happens in a rule declaration. So when you have a simple PCCL rule declaration like that, local tx, essentially what this means in any high-level language today is that you have a variable named x of type t, and the accessibility of this is local, which is it's local to a specific routine, or it's local to a specific entity. But what does that translate to internally when this is executed? The first thing that happens is the control fetches a free address, L, from the mmap. And what is mmap? Mmap is the global lookup for the entire system. So you have an address L that is identified from the mmap, which is free, and it's assigned to X. So X points to L in the agent's memory cell. And now the important point here to note is that within the bounds of an agent, the value X is referenced to L. It doesn't have the value itself, it is a reference. And L in the external memory, which is the global memory, now contains a value which is not set. So it's undefined, but it knows the type of it, T. So it's undefined T in the memory map. And then the instruction is rewritten to empty. So the entire thing changes to an empty instruction. And this is what the K form provides. It rewrites the statement to its bare minimum. So how does this get represented in the state machine? If you look at the rule above, rule variable declaration, it follows a very similar pattern to what we saw in the lookup. So there's essentially 2 parts to it. There's agent and an mmap, right? Everything within the bounds of an agent, that is everything to the left of it, is specific to the agent or the node. And everything to the right of it, the mmap, is on the global level, on the system level. So let's look at it one by one. So within the agent, you have the instruction going in there, tx, which is before the execution of the statement. So it lives above the line, and below the line, there's nothing. It's just a dot, meaning to say that it's empty. And then the next part of the execution is x is set to L, and that happens after the execution of the statement and within the memory of the agent, and the memory cell lives inside of the agent. So that's the next part of it. And the third part of it is the second part, the third part of it is the second fragment of the rule, which is in the M map or the global lookup, where L is now set to the unidentified value of type T. And that lives under the line. So this is after the execution has happened. So all of this that happened as soon as local tx was executed is represented in the form of a state machine automata in the rule above. Okay, so now we get to events and counters. And this is where we'll have to touch upon timing. So, and this becomes important in a distributed system because especially when we're talking about consensus protocols and things like that, because every single node has to be has to provide a consensus on the state of the machine before the next operation can be taken up by the system itself. So let's look at what happens when an event block is executed in real time. You have this follows the exact same automata that we spoke of before. So everything above the line is before, and everything after the line is after the event block is executed. So let's say that the event block is the last line of the event block, which is right there, end event block ... _k. As soon as that line is executed, or as soon as that line is going to be executed, the state of the machine is such that the counter value, remember we spoke about counter, and that is specific to the bounds of an agent, is currently n. Let's say that it's a value called n. And as soon as and the counter map also the counter map has an index I, which is set to n, and this counter map is the global counter map, right? And I is the index that uniquely identifies the agent. Now, as soon as the line end event block is executed, that event block turns to an empty statement below the line. The first line below the dotted line shows that it's an empty statement because the execution is completed. But what happens in the counter of that agent? The n, which was the value of the counter, has now incremented to 1. And in the counter map, the counter value, which is valued against I, which is unique, which is the identifier of the agent itself, is also incremented by 1. And the counter map lives globally on a global scale on the system itself. So what are we talking about here, really? When a bunch of statements get executed within the boundaries of an agent, we are trying to identify or define time with respect to this execution. And this execution, and this time is called discrete time. And this time is specific to that agent. And the definition of this time or discrete time does not, it has no bearing on any of the other n-1 agents within the system or the system on the whole. This is specific to the specific this agent, and that is how the agent computes, or that's how time is subjectively evaluated within the boundaries of the system, right? So, okay. So before we get to the other bullet point over here, consistency and availability and things like that, I need to touch upon the next slide, and I'll come back to this, which is also time. And now we're talking about continuous time. So clearly there's a distinction here. We spoke about discrete time, which works within the boundaries of an entity, of an agent. And now we have continuous time, which is now the global time. How does n number of nodes synchronize within themselves? How do they understand what comes first and what comes next among themselves? So there needs to be a communication that needs to happen, and the communication cannot be arbitrary. The communication has to be synchronous. So for that, we need to define another time called t. Now, this is happening on the state machine that is governing the system itself, and not just an agent. So as soon as the counter map, which is the counter map, is basically the map that gets updated here in the third line, n+1. So as soon as the counter map gets updated, or before it gets updated, the current state of the entire machine is such that the total time is t. And then the transition state is discrete, because because the last line is yet to be executed by an agent. But as soon as that happens, you can see that the entire machine gets updated, and the updated value of it is towards the bottom of the line, wherein your counter map stays Cn, but your time is now incremented by delta, t plus delta. And then your transition state moves from discrete to dynamic or transient. And what is this? So what does this show? What are we talking about here again? This is analogous to having millisecond within a second or seconds within a minute. What we're talking about here is essentially that when two agents are executing asynchronously the same set of code, we have a definition for n, which is basically the amount of time that agent I takes to execute the same set of code, and the amount of time that agent J takes to execute the same amount of code asynchronously. But the issue is, when do they communicate, or who waits before whom? Because there's no guarantee that in a distributed system with n number of nodes, all the nodes execute the same set of code at the exact same time. So there needs to be some kind of coherence here. So what happens here exactly? We identify what is called n naught, and I go back to the previous slide here. And what n naught does is it is a threshold. It's a discrete time threshold that is set on every agent to tell the agent that, hey, if you've executed an event n number of times and your time is n, and if n is equal to n naught, that's where you stop. You stop and wait for the other agents to catch up. And when other agents catch up, that's when you have the global time, which is the transient time or the continuous time of the entire system, acknowledging the fact that all of the agents have achieved their n naught or n equal to n naught, and now it's time for the entire system to go up a notch or go up a tick. Let's call it a tick. So that's what's happening here. So essentially, what we're doing here is when two systems are executing the same thing, there are two ways in which coherence can happen. One is when two systems which are of different speeds executing the same code at different times, one ends up finishing it first and the other ends up finishing it next. We're figuring out who waits for whom. That's one way of achieving quorum. And the other way of achieving quorum is when there is a change in the external environment itself. Now, for example, let's take the example that we've been going with for this presentation, which is a warehouse, an Amazon warehouse, where two robots are trying to sort two packages, right? So there's a package that robot A picked up and is trying to sort, and it's done sorting. And there's a package B there's a package B which robot B is also trying to pick up and sort, right? Now, both of them, there's no guarantee that they're going to end up with the operation at the same time. So what happens here is two things. One, since agent one or robot one has completed the operation, it stops. It waits for robot two to complete the operation. And then the entire system acknowledges the fact that both the robots have finished it, and then refreshes the state of the system. And now we are back to doing it. We're back to rerunning the program for another set of boxes. That's one way of doing it. The other way of doing it is when robot one finished sorting the first box, there is a change in the system itself. There is an external change that happened here. And we need to acknowledge that depending on the use case. So if that happens, every other operations are aborted, and then we hit a hard reset on all of the machines, right? So that goes back to handling conflicts. So what are we talking about again? We have an agent priority system, and then we have an environment priority system. And this goes back to a typical CAP theorem that is quintessential in all modern day distributed systems, wherein you either have availability or you have consistency. In the sense that if you want a high throughput, you want low consistency, and you have high availability or low latency, in other words. But if you want a low throughput but high consistency, you want to wait. So an agent priority system continues. An agent priority system is an n-naught first design, wherein we want to wait. And what do we do by waiting? We achieve consistency. We want to make sure that that another set of operation takes place only after the first set of operation is complete. So what happens here is you're introducing latency in the system. So and it advances only when n equal to n naught. So environmental changes are queued. So there is an environment change happening, but then we don't immediately acknowledge it. We queue it, and then we process it after advancing time. And then there is an environment priority system, which is reactive. And this is a continuous time advance of environmental change, wherein the agent progress is discarded and counters are reset. So what this means is when robot 1 picks up a box and sorts it, we acknowledge the sorting first, or as soon as the sorting is done, before agent 2 can do anything. So agent 2's status is pretty much void, and agent 2 has to start all over again. So what this does is it introduces consistency. You know that the next set of operations is consistent, but there is an issue with availability, because there's weight, intrinsic delay, and latency that's involved. So with this idea, let's just go into a quick simulation. So what we've simulated here is a multi-agent race system, very typical of what the problem statement that I've been describing so far. You have three kinds of entities here. You have the agents, of course, marked by X, and then you have the item positions. Item positions can be boxes in a warehouse. It could be a pathfinding algorithm or something like that. And then you have obstacles. Obstacles are obviously nodes which need not be hit. And these are static. For the sake of this simulation, we've assumed that all of these are static. We don't have dynamically moving boxes. We don't have dynamically moving obstacles, because if that is, that's just going to complicate the overall environment itself. So we don't want to introduce that complexity at this point. A classic example of this, like I said, was a sorting facility in an e-commerce warehouse, swarm behavior. So what does a typical PLCC code look like that conforms to the K framework that we've seen? The first part, this is pretty straightforward. You identify an all right set of destinations. These destinations are all right because all of the agents in the machine, in the system can look at these destinations. All of the machines are trying to fetch these items and can update it. If an item processes, if an agent processes an item, you have to update it. And then you have the other local variables like obstacles, and then a couple of status flags like pick and current destination. Pick basically suggests if the agent is free to pick an item or not, and a current destination identifies which destination it is that the item is located in. Not interesting enough, but the most interesting part is this. You have two agent codes, right? You have pick destination and you have remove. And like I said, these conform to the to the precondition and the effect style that we've wanted in the framework. So what does pick destination do? All it tries to do is it picks a destination that the agent can. It picks a package that the agent is, if the agent is free, can pick. So how do you determine that? You check to see if the precondition evaluates true, which is just a pick flag, right? And if it is, you go back to the effect statements. And in the effect statements, you check to see if there are any packages that need to be serviced. If there isn't, you exit. That's the end of the operation, right? But if not, you pick the head, because you can assume it to be a queue or a stack or whatever. But you pick the head of it and then you do something with it to reach. This can be an external logic. It could be literally having motors which make the robot move, pick up the object and then drop it into an assortment box, or maybe a package or a container which is sorted by zip code for shipment or things like that. We don't really care about do reach because it's a black box at the moment. And then you have a remove. What does the remove do? So once pick dest is successful, all remove tries to do is it updates the shared memory, which needs to be acknowledged by all nodes, right? And that needs to be atomic, which is precisely why we have an atomic block over there. So you pick it up and then you remove. And then you set pick back to true, which means the agent is now free to pick another box. Pretty decent flow so far. But and a quick description on do reach. This is again an abstraction that manages interactions between application logic and physical environments. Not really key for what we have here. But again, we can come back to this if anyone has questions. So let's talk about locking. So you saw that there's an atomic node. There's an atomic nuance there within this subroutine, right? So how do we achieve that? Because you want to be atomic and lock on objects which are shared across many nodes in the system. And when you do that, you need to use a lock, and which is where lock state comes in. We spoke about lock state when we spoke about the K-form of an agent. So this is where a lock state comes in. When an agent acquires a lock, the lock state is set to request or lock, and depending on that, the other agents fall into a queue, which is that's a first in first out lock queue. The other agents are waiting for it, but they cannot because the lock is acquired. So this is where we talk about consistency and all of that, because there's an inherent latency in any atomic operation, which introduces a lock, especially if it is in a shared memory boundary. So what are the results? We see that when we set the threshold and not to a very low number, as expected, we are seeing real-time sync. So all of the nodes, as soon as every node n not equal, we've simulated n not all the way from 1 to 10. So as soon as if you set n not to 1, you have high consistency. All of the nodes are talking to each other more often. As soon as a node completes an operation, all of the nodes want that update. And you have high n not, which is batch processing. This is again a low consistency and high availability model. But when do you use each of these? There's no right or wrong answer here. It really depends on the use case. Is it a financial transaction? You probably want high consistency, which is why when you have a blockchain operation going on, let's say you sell a bunch of Ethereum from a wallet, it takes some time for you to get an acknowledgement that the Ethereum has been sold. Or let's say you transfer Ethereums from one wallet to another. It's not instantaneous. It takes a few minutes. You would take about 4 to 5 minutes before it shows up on your on-chain block and also reflected on your wallet. The reason being that we prefer high consistency design or pattern in financial transactions. But let's assume the typical case of the warehouse example again. Do we want high consistency? Not really. We want high availability. So we can batch process the status of the environment. So this is really what n naught does. It gives you the flexibility to have the system working as both a high availability, low consistency, or low availability, high consistency model. And finally, we run this through a very standard Fisher's protocol. Fisher's protocol is basically a protocol that's out there. It is meant to identify if to validate if a given framework or a protocol adheres to lock contentions. When you have multiple nodes in a typical decentralized distributed system scenario, the first thing that comes to mind is how do we address lock contentions? And Fisher's protocol identifies that. So you run your experiment through a Fisher's protocol. So what happens here is we have two agents, ID1 0 and ID1 and ID 0, and they try to access a critical section mutually exclusively. For starters, we have n naught set to 1, and we have delta set to 1 as well. And delta is not really important, but it really determines the rate of tick of the main system itself. And then you have D, which is the minimum time to wait before you enter the critical section, right? So what happens here is it's typically a flow, but you want to concentrate on the line diagram that you have at the bottom. So when an agent tries to access the critical section, what happens is it spends C1 amount of time to even register an intent to acquire to access the critical section, and that intent, that C1, is randomly generated out of wait time. So you have a wait time on time 0, which is 6 for agent 0 and 3 for agent 1, and then you wait. So the agent waits for wait time number of times to even register an intent to get into the critical section. So you have at cycles 1, 2, and 3, agent 0 and agent 1 waiting. And then at 4, 5, and 6, you have agent 0 continuing to wait because the wait time is set to 6. But agent 1 is already doing something with the critical section. So let's see what agent 1 is doing. So agent 1 assigns a flag called true. And then as soon as it assigns a flag called true, at cycle number 5, it sets the request ID to 1. What is a request ID? Request ID is basically a flag that says that identifies an agent that is that has been the first to register its intent to get into the critical section. So what request ID states here is that agent 1 has registered itself to get into the critical section first. So that's what you see on time counter number 5, right? And now it waits again. It waits for how long? It waits for C2. C2 is 2 because D is set to 2. Now, what do we define D as? D is the minimum time to wait before entering the critical section. So D really determines whether you're going to run into a contention or not. And identifying the minimum D is critical to a system like this. And that's what Fisher's protocol provides. Fisher's protocol is a set of operations that you perform on a framework or a language that you or an algorithm that you propose to identify a minimum D that you will need the wait time to be for lock contentions to not occur. So in this case, at time 6 and 7, you have agent 1 waiting, C2 equal to 1 and C2 equal to 2, while request ID is set to 1 before the lock contention actually happens, right? And then at time counter number 8, you have request ID agent 0, which was waiting all this while, now wants to get into the critical section too. So it also acquires the lock, but meanwhile, agent 1 has already checked if request ID is equal to 1, and it continues to access NCS, which happens to be the resource within the critical section, and it sets it to true, right? So your global memory has request ID going from 1 to 0 because agent 0 has accessed it, but your NCS is set to true. Now, as soon as, and then the natural progression takes place. And again, at time 11, something more interesting happens, which is agent 0 again tries to perform what agent 1 performed at time equal to 8, which is again set in NCS to true. And NCSs are local variables to both the agents. So now at this point, you have a collision. You have NCs set to true for both agent 0 and agent 1 at time equal to 11, which means, and this happens when? This happens when D equal to 2. And this is not seen to be happening for D greater than or equal to, or greater than 2. It seems to be happening for D less than 2, which is why bounded execution results show that this solution fails for D less than or equal to 2, but passes for D greater than 2. And this is expected. So the larger D increases, a larger D increases the throughput, but it enhances consistency because there's less likelihood of collision. Now, how do you scale this? So we have 2 agents here. The last part of this talks about consensus at scale. Now, shared memory can obviously be abstracted out as a data store, which is typically write heavy because it's a lot of all of these nodes registering their status onto the data store. And then changes from an agent AI after the write operation can be propagated to other agents in the system in an event-driven push model. So what that means is an agent 0, after executing and making changes to the shared space, writes to the data store. The data store then captures the event in a typical CDC event-driven data capture model, puts the event into a queue, and then you have a bunch of consumer groups which are subscribed to this queue, and then it could be a Kafka or something, and then consumer group can pull out of this queue and then update the agent nodes 1, 2, and 3, which now have the updated value of agent 0. Now, again, what is the issue here? By doing this, this basically determines if the entire system is consistency heavy or is it availability heavy, and that's determined on how the transition from data store to agent 1, 2, and 3 occurs. It could be a synchronous operation, which means you're preferring consistency, or it could be a change queue consumer group kind of an operation, wherein you're asynchronously doing it on a background thread. So what are some typical use cases that we can think of? A decentralized supply chain management tracking. It could be tracking, it could be verification, it could be ledger services or whatever. It's to enable product tracking, status verification, automated payment release using blockchain smart contracts. The do reach that we spoke about, it can now manage deliveries from one checkpoint to another, tracking items through the supply chain, so on and so forth. Shared variables, what could they be? They represent the production locations, inventory counts, pending delivery tasks. Global locking prevents double spending or duplication of delivery. Confirmations by ensuring that only one supplier or agent can claim a delivery of a package. And then the ledger itself, it acts as an immutable ledger, right? It records every successful delivery, do, reach, done, adding transparency, avoiding disputes, so on and so forth. So the entire operation or the entire logistics of tracking, verification, and ledger can be moved on chain with a decentralized supply chain management. Which is something that Amazon is currently working on. Decentralized autonomous organizations, or DAOs. Implementing a voting system, essentially a governing system, where agents are voters and votes are considered atomic operations on the blockchain. So global locking prevents double voting. An agent cannot vote more than once. Event blocks represents proposal submissions. When one agent submits a proposal, how do we vote if the proposal needs to become a law, or how do we know that this is supposed to be part of policy? Voting sessions and result finalizations, right? Then shared variables. These can be active proposals, proposals which are a part of the global memory. And then immutable records. These contain the voting results itself. You cannot go back and mutate voting results. Decentralized gaming platforms. Think about a turn-based game engine where agents are players, game state changes, and game state changes are managed via blockchain smart contracts. What does do reach mean? The abstraction manages real-time game actions like moving game characters or capturing assets. Global locking prevents race conditions by ensuring one player action is processed at a time, right? Think about chess. Every move is a state. Shared variables or destinations. Track active game positions, resources, power-ups, so on and so forth. It stores and synchronizes game states, enabling verifiable, transparent gameplay. So these are some of the use cases that this can fall into. So to conclude, what have we come up with as part of this paper? We come up with a formal language semantic, an abstraction layer, and a framework for developing application code for multi-node distributed system, specifically aimed at on-chain IoT, automation, and robotics. And then it's multidisciplinary, so it's easily extendable to other areas of distributed systems, swarm technologies, robots, drones, so on and so forth, right? It's robust. It's tested against popular industry standard protocols like Fisher protocol. And then it's scalable. You have n number of nodes. You can remove or add at will. You write the application code once, deploys all over, and then the consensus takes care of itself.